To end this second session on Industry for Life, I'm really pleased to welcome our next speaker, Shahriar Shahramian, Bell Labs. And Bell Labs need no introduction. Shahriar, the director of the Freight and Packaging Research Lab at Bell Labs Nokia Industrial Research. Shahriar is a Bell Lab Fellow and leads the design and architecture of several state-of-the-art optical, coherent, and wireless products. His research focus includes design of microwave wireless and wireline circuits and systems. And networks and systems of systems are truly the key infrastructure of this century, opening for Internet of experiences in need of a lot of science. So please welcome Shahriar Shahramian. Thank you very much.
All right, perfect. I want this talk to be a little bit about this celebration of the science, aside from the technology itself. It's a place close to my heart. That's why I'm at Bell Labs, and I want to talk about that a little bit more. So let's look at the electromagnetic spectrum, gift of nature that's already there, and the human ingenuity that's found ways to leverage and use it to do extraordinary things. We found out that you can communicate by embedding data in the electromagnetic spectrum. That's old. And Braun also discovered back in the 1900s that if you have multiple antennas and you change the signal on each antenna, you can actually shift the orientation, the direction of the beam coming from the group of antennas. This is called a phased array. And of course, Nobel Prize in 1909. Then you can listen to the EM background in a few gigahertz, and you'll get the cosmic background radiation. Nobel Prize, 1978, that tells us that the universe really did start with the Big Bang. It's a signature of the early life of the universe. You can then take photons in the electromagnetic spectrum, in the infrared light, you can focus them, and you can suspend matter, biomatter, called an optical tweezer, without damaging it, by using the photons themselves. Again, Nobel Prize, 2018, also from Bell Labs. You can take the same photons, you can make a semiconductor material that pumps out photons at a very rapid rate. That's a solid-state laser. You can change the phase and the amplitude of that signal, put it through fiber, and get a terabit per second of data. And that would be the record at Bell Labs for the fastest transmission of data over a single wavelength. You can take the photons, put them over the surface of a semiconductor material, convert them to electrons, you get a solar panel. Or you chop it up into individual sections, you focus light onto it, you get a charged coupled device, and you get a Nobel Prize. And then after that, you can take light near UV. You can put a dye in a biomaterial. You can hit it with the photons. They fluoresce back at a different wavelength. You can identify and mark biomatter. You can look at that. You can take that a step further. You get super resolved fluorescence. You get a Nobel Prize. Hopefully, you get the pattern right now. That's also from Bell Labs. This is an extraordinary thing. And this is just a fraction of what is possible in the electromagnetic spectrum and the human ingenuity that goes into leveraging its power. Now let's talk about our network. This doesn't get enough credit. During the pandemic, our entire species collectively changed how we consume data. We used to mobile devices. We used to go to buildings where we worked. We stopped all of that almost instantly. And then we changed the way we use data. We changed what we watch. We changed how we connect. We changed what websites we go to. More importantly, we changed where we were when we were consuming data. So now all of that data needed to go somewhere else. We started using applications at an exponential rate. We're not designed for pandemics. If the pandemics had happened 20 years ago, it would have crippled us, because all the remote work, all the interconnect, all the infrastructure remained up. We talked about the failure of the medical industry not to be able to keep the hospitals running by being overwhelmed. Nobody talked that the network worked. It wasn't made for that. So despite what Dr. Weinberg said, go and hug an engineer. Okay? It's really incredible that these things stayed up and they worked. So we talked a lot about the digital twin, digitization, but the idea here is digitizing the real world has a really interesting consequence. And the consequence kind of can be seen in the philosophy of Wolfram Alpha. If you've ever used Wolfram Alpha, and if you listen to its CEO speak, he says that he wants to make the collective human knowledge computable. Okay? Computable is a very particular approach to data. Now, if you digitize the physical world and you can compute upon it, then time disappears, because computation in the physical world means prediction. Prediction can go forward, can go back, and that changes the way we think about the physical world. But of course, digitizing the physical world is what everybody talked about, but nobody talks about how we're going to digitize the physical world. And that's the part I want to focus a little bit on. These are the 6 key technologies that Nokia often talks about being at the heart of 6G. And if you look at that, 3 of those are physical interface devices. Means 3 of them are literally pieces of hardware that you're going to need to interact with the physical world, whether it's data transmission or whether it is extracting information and understanding what materials and environments are made of, understanding the spatial environment. These are hardware pieces. If you don't have those, you cannot do a digital twin. Okay? You're assuming you have it because you assume all the data is there, but that has to come from somewhere. And the digitization is a key part of that. And once you do that, I don't need to get into the details of that. You know what you can do with it, whether it's in industrial applications or whether it is enterprise application or end user application. So the cellular network was invented 75 years ago. And the first cell phone call was made just over 50 years ago. 50 years ago, that's not that long. And since then, generation after generation of cellular network infrastructure has allowed us to do incredible new things, and up to the point of 5G, which is where we are now. But the networks of 2030 are going to look very different. And there's a lot of AI and ML that's going to be embedded in the network that I want to talk about. And new functionalities built in the network that we were never doing before. So we, as engineers, are constantly flooding our environment with electromagnetic waves, and they're all there at the same time. We either time division them so they don't interact, or we use different frequencies, or we change the polarization, or we just say, no, we're just going to throw it all at the same time, use them all at the same time, figure it out later. That's MIMO. And in what Richard Feynman said, it's really an inconceivable nature of nature, that these are all present at the same time. We never take anything away. And that's the amazing thing. We always just add to what's already there, because we cannot take anything away, because the infrastructure is built on it. So what does that look like in the very, very narrow part of the electromagnetic spectrum used for wireless transmission? We start from 1 gigahertz, really low frequency, 900 megahertz. We go to tens of gigahertz. That's the 5G millimeter wave, which I'm sure you've heard about. And then the goal is to go above 100 gigahertz. And why would you want to go above 100 gigahertz? It's because there is a lot of bandwidth available. And bandwidth directly translates to cramming more information in the spectrum that you have. Spectrum is really, really, really expensive. Billions of dollars are paid by the operators to capture a narrow bit. So they really want to get the most out of their investment. Now, there is a lot of challenges with doing this. There's a lot of challenges in building circuits that are in the upper near terahertz. And in near terahertz frequency range, a lot of other interesting things emerge. In fact, if you go high enough, you'll eventually catch up to the bottom of the optics. That's how you start approaching the infrared frequencies. But in the near terahertz, you can build radars, you can build communications that do 100 gigabit per second over the air, which is the ultimate goal of a wireless system, because it approaches the speeds you can do in fiber. And once you can approach the speed of fiber, it changes the way you can deploy networks. You can put it in places you couldn't put before. So what are our communications of networks actually look like? We have what we call it in Nokia the essential fabric. That's the underlying hardware infrastructure, optics, backhaul, all the wireless, passive optical network, the stuff that gives you internet at home, the stuff that's on your cell phone, the stuff that is the infrastructure, that's all at the bottom. Then there's the functionality that sits on top. That's the 6G communication and sensing part. I'll talk about the sensing a little bit. But as with any system, once it becomes complex, there are emerging properties that you can leverage by having dominance over the entire network, by looking at it as a whole. So you end up with what we call the network of networks, where you now have to manage this extraordinary complex beast that you have created in order to be able to extract additional functions from that, and you wrap around that what we call a frictionless network, which is AI and ML based, to manage this entire thing. If you own a slice of this, it works. But if you own all of it, you can do things you could not do with one piece. And that's one of the nice things about Nokia and about Bell Labs, is this multidisciplinary ownership of a very complex network infrastructure. Let me give you an example of what AI can do, which is unusual. So when it comes to communicating between 2 points, signals that leave a transmitter and arrive at the receiver get affected by the environment. They get affected by the devices that they go through. We have decades of research on how to undo that effect. Okay? That's how we manage to get rid of errors. That's how we manage to equalize and find out how we can connect two things together. It turns out that if you throw AI at this, it does bizarre things, things you wouldn't expect. It starts creating constellations for data communication that are non-intuitive, are unusual, and are constantly changing. These are not pre-programmed. And I want to emphasize that it's very unusual to throw AI at a problem that is so ridiculously optimized over decades, but it works, and it works better. That's called the artificial intelligence air interface. So what is the idea here? The idea is that we are using a lot of bandwidth in the EM spectrum. We have all of this infrastructure that we put in. Why don't we make the infrastructure also sense the environment? But sense the environment without interrupting the communication that is happening. Now, the power of that should be pretty obvious. If we have cell towers and cell phones and Wi-Fi and 5G networks and 6G networks all over, as they communicate with individual users, the data going between the user and the tower tells you something about the nature of the environment that's around it. It's like a radar, but not quite a radar, because you are communicating at the same time. And extracting that information doesn't quite come for free, but it is significantly cheaper than putting sensors everywhere. So therefore, your network also becomes a sensor. What can you do with that? Well, a lot, actually. For example, let's take the automotive case. You can throw as many sensors as you want in a car. You can make the car as sophisticated as you want. It will never be able to see it around the corner. It will never know what's going on in the next street over. But a network infrastructure that's communicating with all the users and also is communicating with the car can model the environment in real time and feed data back into the computers and into the AI machines on the car itself. And it becomes, again, a network of networks. And you can extract information from that. Same thing with environment, localization, sensing. In terms of privacy, what you can do is you can have your network figure out if there is EM spectrum that shouldn't be there, or if it is being exchanged and interacting with the environment in a way it shouldn't be interacting with the environment. That can raise an alarm and can raise additional applications on top. Now, obviously, as a scientist, I hate the word monetization, but monetization is at the heart of everything after all. And here, the way this system would work is you would sense and you would impose actuation on the physical world. So at the bottom, you have all the physical worlds. Then you have all the communication infrastructure that sense the environment, compute it using AI, figuring out what is going on. And then information goes up to the application. So this would be the first time where an application is aware of how the network is built, and the network is aware of how the application operates. And that co-optimization can happen in real time, and resources can move in and out of the network from the cloud, near, far, and edge, and figure out how it should be optimized. This is really a genuinely remarkably complex idea to execute, but it can be done. And the consequences are, of course, quite incredible. So here's a video. This is a joint communication and sensing demo at Mobile World Congress in 2023. And here you can see a person on the left. There is, inside of that wall, a millimeter wave base station prototype that is communicating regularly. And at the same time, the same waveforms that are used for communication are detecting the location of that person as that person walks back and forth. This is trivial to do with a radar. Okay? I want to make sure it is clear that this is not a radar, that this is communicating normally, and the byproduct that information is used to extract the location. And similarly here now, you can have the communication all around, and as you move around, your location can be extracted from the wireless signals bouncing around, and you can have a virtual environment that adjusts your location based on where you're moving by reversing your position from the EM waves. And we also have sensors in places you wouldn't expect, right? So we have fibers in the ocean connecting, in this case, somewhere in the United States to somewhere in France. And this is kilometers and kilometers of fiber under the ocean. Well, it turns out that when you pass photons through a fiber optic, the environment around the fiber also influences what happens to the phase and polarization of that light. And if you run and train an AI algorithm on that, you can then extract what is happening at the ocean floor by how it is affecting the data inside of the fiber. These are already there. Now, if I told you go and put a fiber between Paris and the United States in New York just so I can see what's going on in the bottom of the ocean, that would never work. The economy of it doesn't work. But if you already have it for other reasons and you've been training on the data because it's been there for a long time, now you have a whole other sensor at the bottom of the ocean that you didn't pay for. This is a really important development. Now, building these things is very difficult. I don't need to tell you. This is an example of something we built at Bell Labs. This is a phased array operating at 95 gigahertz. Each of those individual little rectangles you see is an antenna. And this is made of integrated circuits that sit on top of the printed circuit board. If you're not in the field, it's a little bit hard to appreciate. But asking a printed circuit board to operate at 95 gigahertz, it'd be like asking an ant to push a tractor. It just wasn't made for that. So it takes a lot of electro engineering, EM engineering to get this to work. We built a lot of integrated circuits. There's a couple of examples on that. These circuits work all the way up to 170 gigahertz, 170. And these are not like digital processors that you're used to seeing often in terms of silicon. These are all hand-drawn in a CAD tool. And if you're off by a micrometer of your design, the center frequency that you want will not come out at where you expected. It will shift by tens of gigahertz because the frequency is so high. And printed circuit boards do not work at these frequencies. So we put our ICs on glass, which is what we call radio on glass. So the bottom modules that you see are unique in the world. And they are a combination of our own RFICs on top of a glass substrate that we've also designed and simulated and modeled. And since we are here in the presence of Dassault, I'll tell you that we use CST. I say this because I'm looking for a discount. So, and if you want to make the next generation of successful CAD tools in the realm of electrical engineering, I can tell you what you need to do. You need to create abstraction. There is no system, for the first time, in high-speed electronics that's designed today where it is not co-designed between silicon, package, housing, antenna, thermal, mechanical, all together. They're all co-designed together. You cannot design them individually anymore because you will never meet the performance. The days of buying things and assembling them are gone. So if you want to create a software, it needs to capture this end-to-end, right? And here's an example of a 3D drawing coming from CST, where you can see our ICs are there. The entire thing is EM simulated. It takes days of simulation for this thing to work at 140 gigahertz. And if you're ever going to the moon, there is going to be an LTE network from Nokia on the moon. And the reason for that is because communication for future missions in space is pretty critical. LTE is a very robust system, right? And the reason it's the generation older because it's really well understood and robust. But there's a mission scheduled to leave with LTE equipment to the moon from Nokia at Bell Labs, where we would deploy that system there. But the learning of this process is more than just deploying a network. It's also understanding what happens to the electronics, consumer grade, roughly, to make it to a different part of our solar system. How would they work? How would you package them? How would you put them together? How would you manage them? Not an easy problem, but something that's coming up. Now, all of this very much depends on privacy and responsible AI. Because I'm talking about extracting information from the world as people move around with their wireless system. And if it's not managed and handled correctly, if it's not done ethically, if it's not done with security and safety, it is a concern. So there is an ethical AI consortium inside of Bell Labs looking at these things, making sure that things are fair, transparent, users understand what's going on. And then when you deploy this system, it has to come with that trust. Otherwise, we're going to run into a whole bunch of other kinds of problems. I want to tell you one other thing, very close to my heart. So this is a photo of me holding the world's first transistor at Bell Labs during an event where they were doing some restructuring. And I managed to hold it briefly with white gloves so I could take this photo. Very exciting. But what I realized after is that this was in 2017. Right? The phone that was used to take my photo has tens of billions of transistors, billions with a B. That's within one human lifetime. This is an extraordinary fact and something really that we should be proud of being human. But you have to understand there's a double-edged sword here. It is true that when things are sufficiently advanced, they're indistinguishable from magic. But magic, when it's pushed too far, removes the awe of curiosity and that seed of inquiry from the next generation. Things just work. And once you do that, once you push it that far, the new generation, the kids, are not interested in how it works anymore. There's too much abstraction. The magic is lost. And when the magic is lost, they will not chase to push the state-of-the-art forward. And this is a major problem in education today. We are removing the awe by not letting people appreciate how complex this thing is. There isn't a single human being alive. Forget the single. There isn't a group of human beings alive who understand how an iPhone works from end to end. And I mean from semiconductor, from processor, from software, from materials, from cloud, from antenna, from display. It doesn't exist. But this thing is in everyone's pocket. This is not the first time we've done this, but this is the first time this thing is in every kid's hand, looking through the screen, interconnected globally. The consequences of that are not really fully understood. It's an experiment being run today on us. You know, we went from burning witches to burning rocket fuel to leave our solar system. This is an extraordinary transformation. Science is our most committed effort to understand the real world beyond the limitations of our senses, but more crucially, beyond our human tendencies for prejudice, bias, and self-delusion. That is science. And if we don't convey that path forward, something seriously is lost. The French novelist Marcel Proust, he said that the nature of discovery is not in finding new lands, but in acquiring new eyes. It's these new eyes that we need in order to make sure we don't lose the magic. We understand the complexity of what is going on. So I'll leave you with a quote here from Carl Sagan, both as an inspiration, but also as a warning from Science as a Candle in the Dark. So for you to read on your own. And that we really do need to worry about this. And education is our tool to do this. But if you don't do it seriously, if you don't take it seriously, the boundary between misinformation and fear are much narrower than we think. So I really hope that you enjoyed this, what I think is a celebration of human ingenuity, not just for Nokia and Bell Labs, but for everybody. And that you would help me in this. We're ambassadors of our fields, and we need to do our job.
Thank you very much, Shahriar. To Olivier, maybe there's another parameter in the complexity equation, which is the awe to be added, I think. One simple question because of time.
Of course.
So, sensing networks. So, are you saying that networks are becoming the central nervous system of the planet?
Well, that is, if there is enough collaboration, such a thing is most certainly possible. And networks is just one part of our sensing infrastructure. It doesn't have to be the only one, but it is one we are deploying. And wireless signals, and we know how to sense with wireless signals. I mean, that's radar, right? But we want to do it while we're communicating. And the network can become self-aware and self-optimizing. And the power saving and the sustainability of a system that works well like that is huge. So definitely, I think, worth the effort.
Thank you so much, Shahriar. Thanks again.
Okay.
So easy transition after the 6G networks. Let's continue with the networking break. See you back at 3:35, so it's a shorter break than before, for final session of the day. Thank you very much.